Welcome back, everybody. Before anybody asks, I don't have your exams back to you today, but that's for good reason. I was thinking about it, and if I gave them back today, then they'd be due on Tuesday next week. Since my office hours are on Tuesdays, that would mean that you'd only have one chance to meet with me. To like if you wanted to meet with me right afterwards, but like the whole goal of the exam redo is for you to look over it and see where you went wrong before meeting with me. And so I figured it would be better to do that on Thursday. That way you can have the entire weekend to think about it. And then like, because that's usually probably when I expect most people to try and get some time in to work on it. So I'm going to be handing them back on Thursday. I've got them mostly graded anyways. Just need to finish a few finishing touches here and there. But yeah, so those will be back to you on Thursday. Okay. What else? What else? Can't think of anything else. So we'll go ahead and get started. So we learned about the definition of the derivative last time. Specifically, the limit as h approaches 0 of f of x plus h, f of the quantity x plus h minus f of x over h, or the formal definition, which would be the limit as t approaches x of f of x minus f of t over x minus t, however you want to do it. And specifically, if you want to do it at a given value, you'd be using this version that I wrote in blue, meaning that it's just going to be evaluating the derivative at a specific value. So you just change the x's into a's. That's all that changes. So we did it twice. And then the key fact that we learned first was that you are not done computing the derivative. You can't take the limit until you cancel that h in the denominator, which makes sense from our knowledge of limits, in particular that if you were to try and plug in 0, you'd be dividing by 0, which is a problem. So we have to do some type of algebra or something so that we can get through things, get things done properly. So this is where we left off. We were talking about the derivative dy dx for y of x equal, or y equals the square root of 3x minus 4. Y of x plus h would be the square root of 3x plus 3h minus 4. And then we correctly got to the idea that we should multiply by the conjugate, because that will get rid of the square roots, at least in the numerator. So that will become the limit as h approaches 0 of the quantity 3x plus 3h minus 4 minus the quantity 3x minus 4, all divided by h times the quantity square root 3x plus 3h minus 4 plus the square root of 3x minus 4. And I'm not gonna foil in the h. I mean, I could, but the problem is that that's the thing you want to cancel. We want to cancel that h. So we're not going to foil it in, because then we just have to factor it out again at the end. And just to save on space, hopefully everyone sees where I got the numerator, because it's going to be the first term squared minus the second term squared. And then when you distribute the minus sign, that's going to allow us to cancel the 3x's and to cancel the minus 4's, because it's going to be 3x minus 3x. And then it's going to be negative 4 minus negative 4, or negative 4 plus 4. So those cancel. And all we're left with is a 3h up top. So we get this, the limit as h approaches 0 of 3h divided by h times the square root of 3x plus 3h minus 4 plus an additional square root of 3x minus 4. At which point the h's cancel. And then just to save on space, I'm going to plug it. Now that I've canceled that h in purple, I'm going to plug in h equals 0, getting color 3 over the square root of 3x plus 0 minus 4 plus the square root of 3x minus 4. And so, just to write it formally, dy dx is equal to 3 over, that's two quantities, that's two square roots of 3 minus 4, which gives us, since they're like radicals, kind of like terms, you can combine them and get 2 times the square root of 3x minus 4. Any questions on that? Yes.
Would you technically multiply out the radical in the denominator to remove a radical sign from there?
Like rationalize the denominator. You can. Like I know in 126, 127, right? We wanted our sine of 45 degrees. Technically speaking, the sine of 45 degrees is 1 over the square root of 2. But we like to see that as square root 2 over 2. We do not need to rationalize in this class. Like we do need to rationalize. Like we need to rationalize things that we're thinking about. But we don't need to rationalize denominators. That actually brings up a good point that we're going to talk about in this next one. Thank you for bringing that up, which has to do with simplification. If I forget to talk about simplification, please remind me. So, any other questions on this one? Okay, you can leave it like that. Key fact number 2 is that for any given a value, f prime of a represents, or more aptly, it is the slope of the line tangent to f at x equals a. Let's digest that for a second. Let's write that down and then digest that. And then also kind of marvel at how cool that is. And I'll explain why in just a moment. Any given a value, f prime of a represents the slope of the line tangent to f, the original function, at x equals a. So f prime of a is not a line, right? It's just the slope portion of the line. Which is pretty miraculous if you think about it, given our history of functions. Like in Math 126, we talked about like the library of functions. These are what all the functions look like. And we've only really been studying them as mathematical objects. Like, here's the type of function, here's its properties. It's continuous, its domain is everything. It has end behavior that goes up on the right and bottom on the left. But now we actually have a mathematical interpretation of something for more than just its properties, like more than just like its domain and things like that. So where was I going with this? If you look at all these derivatives that we've calculated, these were derivatives for any given xt or whatever value, and they're functions. They're functions. This one right here, function. But when you plug in a specific value, let's just like looking at this graph here, like let's say this was your function for a second, right here. If you plug in f prime of a, you get the slope of that pink line that I just erased and redrew. You get the slope of that line. So the derivative is both a function, and when you plug in specific values, it gives you slopes of tangent lines to that curve. If I can, like at some point, I'll try and mess with Desmos to show you kind of a cool little nifty trick about it to give a little more insight. But that is a really, really nifty thing about the derivative, is that you can think of it as a function, which it is, or if you want to, in certain circumstances, it's helpful to think of it as the slope of a line tangent to f. And this brings up a kind of a reason why I do like Leibniz notation. Could you imagine if you're scribbling this very quickly, your f prime can look like f of x. That's the reason why I also like Leibniz's notation, because it is useful in that aspect. So just so we're clear, this is the tangent line to f. So for f of x equals 3x squared, find f prime of 1 by the definition, and then find the equation of the line tangent to the graph f at x equals 1. So the definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. But if we're doing it at a specific value, then it is the f prime of 1 is equal to the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. Now, because you might be like me, you might not be. I like to compute these things off on the side because I don't like my mind trying to handle too many things at once. I don't like juggling too many things. So I'm going to calculate f of 1 plus h over here. That's 3 times the quantity x plus h squared plus 1, or not x plus 1 plus h, excuse me. And so foiling that out, and you get 3 plus 6h plus 3h squared plus 1, or preferably 4 plus 6h plus 3h squared. Please leave some space over here on the right side, because we're going to write a little note. It's a little reminder. It doesn't have to be exactly there. You can put wherever you can put a little bit of space, but we're going to need about a quarter of that section. Like at least this much space. So the other thing is we do need to calculate f of 1. F of 1 is 3 times 1 squared plus 1, which is equal to 4. I hope you can see, by the way, now why I write out the thing for our notes. I don't require you to write 3 times 1 squared plus 1 on your exams or on your on quizzes and things like that. I don't expect that because I trust you to compute those things. I write them in our notes, especially now that we're dealing with derivatives, so that if we accidentally have a tick mark here, if we accidentally are erasing and then a pencil shaving ends up making it look like there's a prime there, then we look at the computation and say, wait, that must be a smudge. You see what I'm saying? So now that we got that, now we can actually compute f prime of 1. That'll be equal to the limit as h approaches 0 of 4 plus 6h plus 3h squared minus 4, all divided by h. And luckily for us, the 4s will cancel, bringing us to the limit. And if you want to skip algebra, you be my guest, but this becomes 6h plus 3h squared all over h. But as a reminder, we cannot cancel the h's currently because in the numerator, the h's are parts of terms, whereas in the denominator, the h is a factor. And we can only cancel factors. We can't cancel terms vertically. So that's not too terrible, though, because there's a common factor of h. This is h times 6 plus 3h. And yes, I could also factor out a 3. I could do that. It's not wrong to do so, but at the end of the day, I'm going to be plugging in, I'm looking for a number here anyways, so like why bother factoring it out? It's not wrong to do so. You could do it. It will work out, but I'm just trying to cancel out that h only. So that gives you, and I'm just going to save on space. And now that I've canceled the h, now I know I can plug in the limit. Now I know I can take the derivative. So I plug in 0 for h. I get 6 plus 3 times 0, which is 6. Right. Let's recap what we did and then identify why we did it. So we wanted to find the f prime of 1. So the derivative at a specific value. So we replaced all the x's in the definition with 1s. We computed those things off on the side, and then we got all the way down and we got 6. The reason why we did that is because of the key fact number 2 hidden behind my little toolkit, is that f prime of 1 will represent the slope of the line tangent to f at 1. So this is what this is what I like to write as m sub tan. That is my tangent slope. That is the tangent line's slope at x equals 1. Now, it's been a while since we talked about lines, so just as a small refresher, in order to find the equation of a line, there's 2 options. You can either have 2 points, because then from the 2 points, you can create the slope and then go from there, or you need the slope and a point. We found the slope, so we still need a point. Still need a point on f, the OG function. The OG function, the original function, not f prime, but the point on f, because we're talking about a tangent line to f, not to f prime. So how do we get that? Sometimes it's given. Sorry, I'll let you answer that, Chris, in just a second. Sometimes it's given. Sometimes it would say find the equation of the tangent line to the graph of f at 7, 8, something like that. In which case you got the point. Awesome. Other times it says that x equals 1. Other times you might have to find that x value. All depends. But here we're just given at x equals 1. So Chris, how would we find it?
You just plug 1 into f of x.
Exactly right. So yes, to find the corresponding y value, we plug it into the function to find the function value, which is the y value. So I know we computed it in blue, but I'm going to do it again just because that doesn't necessarily always happen. So f of 1 is 3 times 1 squared plus 1, which is 4, which gives me the point 1, 4. So I've got my slope and I've got a point. That means I can create the equation of the line. And just as a little refresher in side note land, line equations. There is, for whatever reason, everyone's favorite, which is slope-intercept, which is y equals mx plus b. That's everyone's favorite for whatever reason. They're wrong, but whatever. The better version is point slope. And I'll explain why in just a moment. Does anybody remember point slope form? No? Well, you're going to need it. It's y minus y sub 1 equals m times x minus x sub 1. That is point slope form. Yes, it's more to memorize, absolutely, but because there's more letters. But you can go from point slope form to slope intercept form by just simplifying. You cannot go you can go from slope intercept form to point slope form, but it is very contrived and very, very technical and annoying to do so. That is why I don't recommend doing it. It can be done, don't recommend it. The other reason, which will be highlighted very shortly, so I'll talk about that in a second. Now, I will say there is a reason to use slope intercept form. So use slope intercept if you're going to do something. With the tangent line. This is a good rule of thumb for the rest of our mathematical career here. I am one of those people, you'll once we start getting into section 2.2, 2.3, 2.4, whatever, you'll see that I don't require you to simplify. I do not require simplification on my derivatives and anything like that. I'm not testing you on your algebra, I'm testing on your calculus. That being said, if you're going to do something with your derivative or do something with your slope intercept, with your tangent line, that is when you want to use your simplified form, because that's going to be the easier form to work with because it's simplified. So that's the rule of thumb, is if you're gonna be doing something with your derivative or your tangent line or whatever, make sure it's in the simplest form you can. That way it's easy to work with. But if you're just going to be asked for the tangent line, just leave in point slope form. Because most of the time when it comes to derivatives and finding tangent lines, you're gonna find the slope and the point. So you're done if you use point slope form. Whereas with slope intercept, you'd have to solve for B. Unless you get that very, very, very rare case where you have the y-intercept as your point, which is 0% of the time. So that means using point slope form, we have y minus y sub 1. So y minus 4 equals m, which is 6, times x minus x sub 1, which is 1. Or if you do want to write it in slope intercept form, y equals 6x minus 6 plus 4, so that's minus 2. Just because I'm petty, I'm going to box this one in dotted lines to say that it's less good. Agreed, 100%. Much like my brother. No, I'm kidding. I'm kidding. My brother's very successful. Yeah, he won't see this. He makes more money than I do. He chose the smart career, mechanical engineering. Anyways, I'm not jealous. He doesn't get free food for lunch every day. Sushi, by the way, sushi, and he works for a company that's a contractor for Google. You know the people at Google get free haircuts and massage credits. There's a reckoning coming for that area. The scene in The Dark Knight was like, soon you'll realize that you shouldn't have kept like how you could get so much without giving anything to the rest of us. Anyways, I'm getting sidetracked. Not important. Any questions on this one? Yes.
The first part, the blue,
Mhm.
instead of doing it that way, you just find the derivative of x and just plug it in.
Excellent question. Absolutely correct. Yes. So Hiroi, right?
Yeah.
Hiroi was saying, couldn't we just find f prime of x off the get-go and then just plug in 1? Absolutely. I wanted to do this way for a specific reason so that we're comfortable seeing this, because in certain scenarios, you'll see something like this in an abstract situation where you can't actually find the derivative by algebra. And so we have to know what that looks like. That's the main reason, just to be comfortable with it. But absolutely, that would be the faster way to do things, especially once we get to section 2.2. So next one, the derivative of y equals x cubed minus 2x plus 5 is 3x squared minus 2. You can use that without proof. I don't want to get us bogged down. So we're going to determine the equation of the line tangent to the curve at the point 2, 9. So this one already gave us the point. So for the equation of a line, you need a slope and a point, or 2 points. Here we already have one of the points, and we can use the derivative to find the slope. So slope over here, y prime is 3x squared minus 2. We're going to find the tangent line at 2, 9, so we're going to use the x value 2. So y prime of 2 is equal to 3 times 2 squared minus 2. So y, which equals 3 times 4, 12 minus 2, 10. That is our m-tan. And the point was already given. Smiley face, so we don't have to do any work, as 2, 9. So we're all done. I'm going to rewrite the equation for point slope form just so you practice with it. If it's still rusty. Once again, you can write your equation in either form. I will never ask you on an exam or on a quiz to write your lines in a specific format. I don't care about that. Either way is fine. Just use the rule of thumb that I suggested up there. If you need to use it, convert it to slope intercept. If you don't, just write it in point slope, because this is all I have to do. So y minus y sub 1 equals m times x minus x sub 1. That is y minus 9 equals 10 times x minus 2. or y equals 10x minus 20 plus 9, so minus 11. Yeah, I am that petty. I'm gonna do it every time now. It's the first time I've started doing that. I'm gonna do that forever now. So I want to show you why I like that for, like, I'm going to show you the difference. If you wanted to do with the y equals mx plus b, you would have to do this. You would have to go, okay, y equals 10x plus b, and then I'd have to use the point 2 comma 9. That's x and y. So I'd have to have 9 equals 10 times 2 plus b. That gives me negative 11 equals b, which means now I can finally write my answer. Way longer. I was able to write it in one line instead of 4. That's why I like slope-intercept form. Point-slope form. Another reason why is this tells me exactly where the tangent line is. If I have it in this form, I have to draw that line to figure out where the tangent line is. So like the curve y equals x cubed minus 2x plus 5 looks something along this line. Something like that. Something like that. If I were to use this form, I would have no idea where it was until I finally drew it and drew it nicely enough so that I could be like, okay, there's the tangent line. Whereas with this format, it tells me exactly the point, 2 comma 9, because it has the point listed, the x value and the y value. So it tells me, okay, so it's right here, and the line has a slope of 10, so I can draw it. That's the reason why I really like it, is it tells you immediately where the tangent line is occurring in relation to the graph. That's another reason why. So anyways, any questions on that? Okay, last one, super fun one, super fun. The derivative of a function, f of x equals 1/3 x cubed minus x squared minus 7x plus 2 is f prime equals x squared minus 2x plus 7. We're going to use that, or minus 7, use that without proof. Determine the points where f has a tangent line of slope 8. Okay. Haven't encountered one of these problems before yet, so it's a little bit daunting, at least at first. But, wait, sorry, I want to make sure. Did I put another problem on here? That on the next section? Sorry, I just want to make sure. That's a really good problem. Yes, cool. We'll get to it. I was worried there for a moment. All right. So determine the points where f has a tangent line with slope 8. So let's interpret this. We want our tangent line to have a slope of 8. That means we want mtan to equal 8. We want the slope of our tangent line to be equal to 8. But mtan is f prime of a. So these are all equal to each other. So what we're really saying is we want to find, so from orange, we want to solve f prime of x equals 8. That's what we're being asked to do. Inadvertently, like subtly, we're being asked to find, we're asked to solve f prime equals 8, because if we solve that, we're setting the derivative equal to 8, which is the same thing as saying the derivative, the slope would be 8. So f prime of x is x squared minus 2x minus 7. We're going to set that equal to 8. And then from there, we've got to bring all the things to one side so that one side is 0. Get x squared minus 2x minus 15 is equal to 0, which gives us x plus 3 times x minus 5 equals 0. And by the way, since we're not going to really use the factorization at all here, you could probably just use the quadratic formula if you want. It's all right to do so. And you get x equals -3 and 5. And silly John Doe student, he boxes this in. Why is John Doe student going to get an 8 out of 10? very close. He needs to, like, those are the X values. The question is asking for the points. So we need to find the corresponding Y values by plugging them into the original function. So, classic John Doe. Silly kid. So f of -3 is 1/3 times -3 cubed minus -3 squared minus 7 times -3 plus 2. And yes, I'm writing it out. You wouldn't need to do that on a quiz or an exam. You could just use your calculator. I'm just doing it so that when we're looking back at our notes, we understand how, like, what we plugged it into. And I don't have that off the top of my head, so I mean, -3 cubed is -27, but anyway, let's let the calculator do the heavy lifting. -9 minus plus 21. Oopsies. Nope, come on. -9 plus 21 plus 2. You get 5. And then from f of 5 now, in a similar fashion, you get -125 divided by 3 minus 25 minus 35 plus 2. Did I do that right? I think I did this wrong in my other class. I think I made changed a minus sign. Oh well. Their loss. All right. Is that what anybody else gets? -299/3. Not sure. It should be -299/3. By the looks of it. Why am I not liking that? That looks just so weird. Oh, because I put in a negative. That's what's going on. That's not right. So that's not right. There we go. That's looking right. -49/3. So we have the points -3 comma 5 and the point 5 comma -49/3. Any questions on that? So you can find them, you can find specific X values and points, therefore, where your tangent line is going to have a slope of 8. Any questions? All right. Oh, yes.
So
Okay.
how much test you wouldn't get marked off for just giving that in your calculator?
Mhm. Yeah, absolutely. You can plug it in and write like f -3 = 5, and I give you like that would be fine. Big check mark. All right. The last thing, so how do we utilize this? Math must be useful for something. Not much, but something. In a real life sense, the derivative can be thought of as the instantaneous rate of change. So for example, as opposed to finding your average speed over the course of a road trip, you could instead find out how fast you are going right now. That's how your odometer kind of works. Like there's a little bit of math going on in the background. And so this becomes especially useful in many fields, most importantly physics, because physics is just applied mathematics. And so in that context, the position of an object, whether it be a particle or a car or whatever it is denoted by S of t. Why they didn't use P of t, I have no clue. Classic physicists. I mean, do you know what this shape is, guys? No, that's what the physicists would call it. That's actually a torus. That's the real name for that. The physicists call it a donut because they're amateurs. No, that's ridiculous name for it. It's a torus. So anyways, Physicists, for whatever reason, they called the position function S of t. Don't know why, doesn't matter. And then the derivative of that function, if you take your position and you take the derivative of it, you get the velocity. The velocity of the object, which is denoted by v of t. See, now they're starting to make sense. V for velocity. I really don't know why they have to do S, but anyways. So in that regard, S prime of t is equal to V of t. I say that because that's kind of a confusing thing, because when we write velocity, we're going to be writing V of t, which is a derivative of the position. So just know that in order to find the velocity, you take the derivative of the position. We're not going to do too many physics applications because this is a math class, but every once in a while we throw one in just for funsies. Because who doesn't love doing physics? This guy. I've never taken a physics course in my life. I'm sure it's fun. But I've just never taken it. Yeah, I like it. No, I've wanted to take it. I've wanted to take it and just like pretend to be just a random
You
dude.
do like 181.
I've always wanted to. I've always wanted to just take someone else's 181 and just coast through it. That'd be awesome. So sorry to get sidetracked. Differentiability. So that is the concept, like in the same way we say something is continuous, we will say things are differentiable. So for any function, we say that f is differentiable at x equals a if f prime of a exists. And the abbreviation, by the way, for differentiable, just so we don't have to write that out every dang time, is DIFF apostrophe. Yeah, apostrophe BLE. Diffable. Differentiable. And that's what I'll be writing because I don't want to get carpal tunnel. And then as an extrapolation of that, if the function is differentiable on the whole real line at every x value, then we say it's differentiable everywhere. But what does it mean to be non-differentiable? What would be if you weren't differentiable? So discontinuities, that is the first type of differentiability issue. So I want you to draw 3 graphs. It doesn't really matter the scaling at all. I'm not really going to draw any scaling. I just want 3 nice and neat little graphs. I get to do this. And I'm going to need 2 in the next row. And then 1 in the last row. Oh, why not? Let's try to make it all nice and pretty. So I'll let you draw all those graphs so that we can, so that you're not frantically trying to get them created while I'm drawing them. So, and then people watch the recording, sadly, you won't be able to see this as well. You won't even be able to see it at all. So please ask me a question if you're watching this, like feel free to come before class, after class, or whatever. So first thing, so discontinuities. So you could have, let's say here is A, you could have a jump discontinuity. Something like that. You could have a hole. Or you could have, an infinite discontinuity. You could have something like this. Oop. Any of those things would be possible. Now, why would it be that it doesn't exist? Why would it be that the derivative doesn't exist at A in this case? So imagine this is your tangent line, this red pen.
Then, if I'm drawing a tangent line, the slope exists, like the line exists here. So it has a tangent line, so it has a slope, meaning the derivative exists there. Derivative exists, derivative exists, derivative exists. But then at A, on one side, I have a slightly, on one side of A, I have a slightly positive slope. It's kind of very, very shallow, but it's still positive. And then on the other side, I have a negative slope. And remember, at the end of the day, a derivative is a limit. The limit is h approaches 0 of f of x minus plus h minus f of x over h. So if the two sides of the limit do not agree, then the full limit does not exist. That is one reason why. Now, it's a little bit harder to understand with A, because the limit does exist. So like the limit of the function does exist. You draw a tangent line here. You have a tangent line, you have a tangent line, you have a tangent line. And then at here, it looks like it's fine, but there's a problem. There's a problem with this one in particular. Think back to the definition. I'm going to write it up here. You don't have to write it. The limit as h approaches 0 of f of a plus h minus f of a all over h. There's a hidden assumption here. It's that if f of a doesn't exist, then you can't compute this. So there's if there's a hole here, f of a doesn't exist, and therefore you can't actually create it. The same is true even if you plug in a point. Yes, f of a would exist, but then you're trying to create a tangent line between a point that's above the curve that's not actually on it, and you're not actually drawing a tangent line. Does that make sense? So that's why that type of discontinuity doesn't work. And then in a similar fashion, infinite discontinuities, drawing it with your pen. On one side, it's starting to go vertically, which means that it would be infinite and wouldn't exist because infinity is not an actual number. And then even on here, it's a negative infinity. It's slightly tilted that way. It's negative slopes, infinitely negative slopes. So those are one situation where you're not differentiable. The other ones are what we call corners and cusps. So this is going to be a corner on the left, and this will be a cusp on the right. Corner, pretty intuitive, right, just by the name of it. So it would be a function like this. And it doesn't need to be such a jagged corner either. But here's A, here's that corner. By a similar discussion about the tangent line, if you look, like if you're approaching the tangent line, like drawing the tangent lines on the left side, you got a positive slope, but as soon as you hit A, it swaps to being negative. So it doesn't, like the left and the right hand limits do not agree, therefore the full limit doesn't exist. And as I was mentioning, it doesn't have to be such a steep corner. It could be just as easily as this. Or like that. It still won't exist because on one side you've got that slope, on the other side you've got that slope. So it doesn't have to be such a dramatic corner, but either way. And then a cusp is something we might not have heard. Yes, Chris.
For the corner, could we not have a number of tangent lines at different angles?
So you could have a left-handed tangent line and a right-handed tangent line, but no actual tangent line exists there. Because you'd be teeter-tottering. Like you could let's see here. Because there's there's an argument to be made here that technically speaking, what a tangent line is a point that touches it locally at one point. So you could draw it. So I guess technically speaking, there are infinitely many. And that might be the problem. It might be the problem because you could draw one here, here, here. All of them work. So there's no definitive one. Excellent question. Very, very good question. Then a cusp is something like this. Oop. That's the cusp, that little point. For a very, very similar reasoning, but instead of having like a definitive slope like the corner does, it's positive here, negative here, it's some value we don't know because we're just drawing a generic thing. But here, it becomes more and more and more negative, more and more negative until it's basically infinite, and then but negative infinite, and then it switches, becomes positive infinite, and then levels off. So Those are cusps. That's another reason why it's not differentiable, because on one side and the other, both sides, it doesn't really work. And then a vertical tangent line. These are one of the hardest ones to see because it's very hard to draw. But what they end up looking like, so I'm going to draw the point here. Here is A. And it's because I want to draw this nicely. So it almost looks like this function isn't a function because of the vertical line test. But if you do get really granular, you'll see that it is not a vertical line at all, right? It looks like a vertical line, so fail it. But it's really hard to draw these things. X cubed looks like, the cube root of X looks like this, and it passes the vertical line test, but at 0 for X cubed root, you end up having this, this vertical tangent line. Oh. And as we've learned, vertical lines have undefined slopes. And so what that's saying, if the slope is undefined, since the slope comes from the tangent line, means the tangent, that comes from the, say that one more time. Since the slope is undefined and the slope comes from the derivative must be undefined. Any questions on that? So those are the different things. So you might be asking then, well, what does differentiability look like? These are all examples of what isn't differentiable. But what does differentiability look like? Hard to describe, and you don't need to draw this picture, but I just want you to see it. The intuitive definition is that it's a smooth curve. It's very smooth. It's not jagged at all. So something like this. That would have a derivative everywhere. That would be differentiable everywhere because it's a smooth curve. Everywhere I can draw a tangent line and it's all fine. So that brings us to a theorem that says that if a function is differentiable, then it must be continuous. So differentiability implies continuity. The other direction is not necessarily true. So this should actually say notes. Note number 1 is that reverse is not true. Continuity does not guarantee differentiability. So continuous does not necessarily mean, it could be, right? This curve is continuous everywhere and it is differentiable everywhere, but that's not guaranteed because you could also have this example. This function is continuous everywhere, but it's not differentiable at A. The other implication is a logic thing, by the way. Like once again, if you have the chance in college to take philosophy of logic, highly recommend. Very fun class, very, very mathematical in nature. And it talks about how to structure arguments and truth. If something is true, what other statements can you make that are also true? And one of the things is called the contrapositive. So the classic thing, like you don't need to write this down, but this is just a little bit of philosophy of logic for you. Usually a statement arrives at this: if P, then Q. If P, then Q. If that is a true statement, the reverse direction, which is called the converse, is not necessarily true, but the contrapositive, which is if not P, then not Q. Sorry, if not Q, then not P. That is also to have the same truth value, is what we call it in the philosophy of logic. So if P implies Q is a true statement, then not Q implies not P is also a true statement. So in the context of mathematics here, this theorem tells us that if not continuous, then not differentiable. That would be the contrapositive of that statement. So the original statement is if P, if differentiable, then Q, continuous. So if not Q, if not continuous, then not P, not differentiable. That is the way we use this one. This is the way we use that statement in particular. So that if it's not continuous, then it's not differentiable, which we saw up above in that first column, or first row. So if you're not continuous, then you're automatically not differentiable. All right. If we have time, maybe we'll go over this. Just ignore this page for now. These are very technical examples. Maybe I'll make a little video on this. You're not going to be tested on this one, but it is an important understanding of the derivative, but we'll get to that later. Graph problems. Thank you. Thank you. I appreciate it. I appreciate it. Graph problems are the best problems. As you saw in the first exam, there's a graph problem. Every exam will have a graph problem, at least one. Because I am cuckoo for graphs. I think they're the best problems to do. So this is the function f. And then at which values is f discontinuous? That's a 1.5 question, but just to give us a little more practice, since the final exam is cumulative, let's go through it. We're looking for jump discontinuities, removal discontinuities, and infinite discontinuities. So going left to right, we get x equals -4, 2, and 5, and that's it. And this is before I could add arrows, so we'll add them on. So those are the discontinuities. First one's infinite discontinuity. Second one is a removable, and the third one's jump. But that doesn't really matter. We're not being asked to do that. At which points is it not differentiable? Now, that starts off with x equals -4, 2, and 5. We already know those because f discontinuous. And you can also just reason it by what we were doing with our pen, drawing the tangent lines. You'll see that it doesn't exist there. Just like on this one, if I'm trying to draw tangent lines at -4, on one side it's going to -infinity, on the other side it's also going to -infinity, but in a different way. F of A doesn't exist, so you got a problem there. So those are all the discontinuity ones are non-differentiable, but then we have a couple more. We have a cusp here at -1. Cusp, and at 5, 6, 7, 8, 9, at 9 for a corner. Any questions on those? Yes, Chief. Nope. So if you are discontinuous, you are automatically not differentiable. Excellent question. But yeah, like if you are discontinuous by design, you will also be not differentiable. Now this problem right here, very fun, very fun. C is very, very fun because it gives us a lot of being able to take in a graph and read it and understand it. So I'm going to underline this in orange, and someone give me another color that isn't orange, brown, blue, or purple.
Green.
Green. Excellent. Okay. So find the values of f prime of -7 and f prime of 8. This is the graph of f. This isn't the graph of f prime. What are we to do? You have a good
Slope.
exactly. Look for the slope of the tangent lines there. So at -8, oh, that was in orange. So at -8, if we draw a tangent line, so f prime of -8 is the slope of this tangent line. M tan equals 0 because this is a horizontal line. Brianna?
That's looking for -7.
7, -7. Sorry, that I can count. I can count. Since M10 is equal to 0, that means that f prime of -7 is equal to 0. And I'm pretty sure I said Brianna, but it's not Brianna. It starts with A, right? I can't remember. Aubrey. Thank you. I'm learning them, guys. I'm gonna get there soon. So because we drew a tangent line there and has a slope of 0, that means the derivative is 0 there. Now, similarly, and the next one was f of 8. So here is 8. Here's the point on the curve, and then this would be the tangent line. It just so happens that when your function is a line, your tangent line is the same line. And so what we need to look at is look for rise over run. So the rise, you can find it any way you really want to. I'm gonna do it from here. That's a rise of 4 over a run of 2. So f prime of 7 equals 4 over 2, which is 2. Now, sometimes it's very, very immediate by looking at the curve because they're nice, neat, organized points. Other times it might be more difficult, and that way you'll use the slope formula. I suppose I'm not going to be too much of a jerk if you're trying to find it with a slope and you don't remember the slope formula, just ask. Bop you on the nose a little bit, but any questions on that? So we're looking at the slopes of tangent lines because the slopes of tangent lines are the derivative at that point. So f prime of -7 equals 0 and f prime of 8 equals 2. Any questions on that? Yes. Oh, sure. And let me like, is that okay like that? I know it's kind of small writing, but if anybody needs me to zoom in, then let me know. All right. I think it's a perfect time to take a little bit break before we get into 2.2. So let's take a break. Not Siri. Let's take a break until 10:05. Let's take a 7-minute break. People watching the recording, go do some guided meditation. Highly recommend. And we're back. So on to 2.2. We won't finish it today, I don't think so, but we'll get decently far. Hopefully we'll get to the very last question because that one's awesome. Really like that question. It's a great question. 100% coolest question in this class. So mathematicians figured out the definition of the derivative, and they said there's got to be a faster way. There's got to be a less tedious way, because doing this right here for problems seems very tedious. In addition, that's just with the square root. What if your function was this? F of x equals x to the 100th plus 25. Would you want to do x plus h to the 100th power? You guys want to do that? Sounds like a fun Friday night, in my opinion. But I mean, you could bust out Pascal's triangle, right? You guys remember Pascal's triangle? That's Pascal's triangle. If you don't know about it, it's really cool. Pascal was a mathematician that figured out that like all the coefficients of a polynomial end up being these numbers and then times the powers. But anyways, super cool. So you could do that. You could write out all 100 levels and then figure it out that way. Or you could fool it out. That would be a fun day. But there's got to be a faster way. And so mathematicians started figuring out proofs of things. So we have, these are our basic quote unquote differentiation rules. Not to mean that they're easy, but to mean that these are the foundation upon which other derivative rules will be formed. So there's the constant. I'm going to draw a dashed line underneath all of these so that I can do an example on the right, but you don't have to. So the constant rule says that d dx of c is equal to 0 for any constant. The derivative of any constant is 0, and the derivative and d dx of a times x is a. So the derivative of any linear term, ax, so 7x. So I'll give you some examples here. Example, d dx of pi equals 0. The derivative of pi is just a number. 3.141596939, blah, 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 blah. Derivative is 0. The derivative of natural log of 7 is 0 because natural log of 7 is a number. And then another example, d dx of, let's say, negative 2x is negative 2. You can prove that, you can prove the linear rule. I gotta change that. It's a backwards quotation mark. Okay. The linear rule can fit into the power rule, but it's better to see it this way in my experience so that you see exactly how it works. So those are the first two rules. Then the next one is the power rule, the most important one out of all of them, in my opinion, because this one gets used in every situation. Almost every situation will involve a power rule in some way, shape, or form. So the power rule says that d dx of x to the n equals n times x to the n minus 1 for any number. So to give you two examples, d dx, as a reminder, d dx is an operation on something. So d dx of something is needed. So you don't want to put the d dx at the right-hand side because that would be that would not be valid mathematics. That would be writing the square root after the number. You don't write 4 square root, you write square root 4. So d dx of 4 or whatever. So d dx of x to the 7th would be 7x to the 7 minus 1, which would be 7x to the 6th. That is the power rule. Another example, d dx of x to the square root 2. Square root 2 is a number, so it can be an exponent. I mean, anything can be an exponent if you really want it to. But either way, this would be the square root of 2 times x to the square root 2 minus 1. And that's what we'll leave it because we cannot combine the square root 2 and 1. They're not like terms. They're not like radicals. So we have to just leave it in that form to be exact. You could write an approximation, but it would be an approximation. It wouldn't be exact. So like you just leave it like that. Does that make sense? So it can be done not just with integers, but also irrational, rational, and integer numbers and negative numbers too. It works for anything. Proving it for integers, not too terrible. Not too terrible. Proving it for negative, sorry, I meant to say whole numbers. Proving it for negative integers, slightly harder. Proving it for rational numbers, slightly harder than that. Proving it for irrational numbers like pi, square root 2, and so on and so forth. That is where it becomes very, very mathy and annoying. But if you want to see the proof of any of these things, please feel free to ask. We don't have time to go over them, but if you want to see the proof, I'm happy to show you. There is a mathematical justification as to why that works. The constant multiple rule is that if you have a function being multiplied by a constant, so that is if you have d dx of c times f of x, that is equal to c times f prime of x. So you could just find the derivative of the function and then multiply it by c it afterwards. Very nice property to have. If that didn't work out, it would be a lot more annoying to compute derivatives. And then the sum and difference rule is that d dx of f of x plus or minus g of x is equal to f prime of x plus or minus g prime of x. Stating that we can take the derivatives separately and then add and subtract them. Very nifty thing. Now, what we'll see later on is that multiplication and division don't have as nice of rules. They have a thing called the product rule and the quotient rule, but we'll get to that in 2.3. Those are the basic ones that we encounter. And so now let's put it to use. When we first do these, I'm going to show all the nitty-gritty details. However, I would like you guys to get to the point where you can just do these ones with mental math in your head. And I'll show you how you do that in a second. So find the derivatives of the following functions. We're going to show all the details now and then start skipping them later, quite quickly, actually. So f prime of x. The sum and difference rule tells me that I can just take the derivative of each one separately. And then the constant multiple rule tells me that I can just ignore the 3. So f prime of x will be 3 times, by the power rule, 4x to the 4 minus 1. Minus that 5 can be ignored for now and take the derivative of x cubed. That would be 3x to the 3 minus 1. The x squared doesn't have a constant in front attached to it, so we don't need to worry about the constant multiple rule. We just take its derivative, which should be 2 times x to the 2 minus 1, minus the derivative of 2x by the linear rule, the part 2 of the first rule would just be minus 2, and then the derivative of constant is 0. If you feel comfortable skipping this step and going to the next one, which is the correct answer, which would be that f prime of x equals 12x cubed minus 15x squared plus 2x minus 2. If you feel comfortable skipping to right there, I need you to be able to do that. Doing this would take way too long in the long run. We're going to be dealing with a lot more complicated derivatives, and that will just really bog you down. So if you want to know the way I do it quickly, so I'm looking at it, I'm going, okay, this is a power rule, so 4 times 3, that's 12, and this gets reduced by 1, that's why it's the third power. 3 times 5, or 3 times negative 5, rather, that's minus 15, and then 1 less power on the 3 would be squared, and so on and so forth. That is what you get to do after a while. Oh, okay. With enough time, you get hashtag get good, like that. Just takes a second. Now, any questions on that? This is one of those things, by the way, this is right now is where we're going to start snowballing. I want you to go home and 1 second, Chris. I want you to go home, please, tonight. Just practice a few. I've got several examples right here, that I need you to practice. I really do, because the next section, the product rule and the quotient rule, we're going to be taking derivatives of more complicated things. So if you can't take those derivatives, you will be SOL when it comes to this section. So please do a little bit of practice. Obviously, right now, study for the quiz coming up on Thursday, which is only on 2.1. But after that, take some time to really practice these, because they're going to get used in multiple, constantly. Yes, Chris.
So you get the minus 2 at the end.
So that would be the derivative of negative 2x. And that's by the linear rule up here. So you can, but that being said, I added that this semester because a couple students got a little bit weirded out by it. You can prove it with by just the power rule. The derivative of 2x by the power rule, that's 2x to the first power. And so by the constant multiple rule, that's a 2 times 1 x to the 1 minus 1, or 2x to the 0, and anything raised to the 0 is 1 is the first power, is just 1. Same for 0 to 0, but we'll ignore that for now. So that's another reason why, the justification. Excellent question. Now this next one. Oh no, we haven't seen that before, and there's no rule up above that deals with that. There was nothing that said, there was no radical rule. But there's a power rule, and every radical can be rewritten in exponential form. So this is equal to, so no radical rule, like convert to exponential form. And just in case you need another refresher about it, you don't need to write this if you know it. The nth root of x to the m is x to the m divided by n. If you want to convert to exponential form, power goes above, the power on the x goes above, the root goes below. So g of t is therefore t to the 1/3 power plus t to the 2/5. And I know they're fractions, but fractions are people just like you and me. We need to be able to use them. We need to be able to work with them and have fun with them. They're just people. It's not very nice to not like fractions. Remember, I was teaching class for elementary school teachers. I was a TA, and then like the main teacher came in and he was very quick-witted. Student was saying, like, I hate fractions, because they were trying to be a math teacher for elementary school kids. And like he overheard them talking in a group project, and he said, I hate fractions. And he went back and said, then you're in the wrong class. You're in the wrong profession if you hate fractions and you're going to teach them. So don't be like that student. Fractions are awesome. Now, so I'm going to do it again. I'm going to do it the nitty-gritty details, but if you feel comfortable skipping that, please do so. This becomes 1/3 t to the 1/3 minus 1 plus 2/5 times t to the 2/5 minus 1. And the trick being, I'm going to immediately write this. I'm going to immediately write the answer. G prime of t is 1/3 t to the negative 2/3 plus 2/5 t to the negative 3/5. The way I did that so quickly is it's always going to be subtracting 1. And you can write you can write 1 as number over number. So in particular, in the first situation, I'm going to rewrite it as 3/3. And here I'm going to write it as 5/5. They'll have the same denominators, so I just subtract the numerators. So 1 minus 3, that's -2. 2 minus 5, that's -3. That's the trick to do it quickly. You're also allowed to use a calculator in this class. So you could do that on your calculator, especially if it's a nasty fraction. Maybe if it's like 175 over 23,000 and you need to subtract 1, maybe then use a calculator. But the more you do this, the quicker you get it, I promise you. The more you practice. And as a reminder, once again, for extra practice, if you want more than what I have a link at the very bottom for Paul's online notes. He has sample problems that you can do that have solution guides to them, so that you can do them and check your work right after the bat. All right. Any questions on that? 30 minutes, we should be good. So h of z is equal to z squared minus 3z plus 1 times z cubed minus 1. Note, sadly, ddx, I'm going to use an abbreviation. I'm going to write f times g prime to mean the derivative of f times g is not equal to f prime times g prime. Sadly, that's not true. Not like with limits. Limits, the product of a limit was the limit of the product, right? You could go backwards and forwards. That is not true when it comes to derivatives. Derivatives don't work as nicely. And similarly, f divided by g prime does not equal f prime over g prime. That's not true. If you do that on the upcoming exam, so like not upcoming, we got like 3-4 weeks. So it's not upcoming. I guess it is technically, but if you do that on the exam, you'll get a 0 on that problem. So don't do that. It's not true, sadly. I wish it was, because that would be a lot simpler, but math isn't always nice. So need to simplify first. Now, granted, once we get 2.3, you will be able to do it without simplifying. But right now, we don't have that tool, so we have to do it otherwise. H of z, when we FOIL it out, got to bust out our distribution rules. So that'll be z to the 5th minus z squared minus 3z to the 4th plus 3z plus z cubed minus 1. And I'm just going to rewrite that in descending order. You don't need to if you don't want to. Like, I'm not going to mark you down for not writing into descending order, but doesn't hurt to do so. That's z to the 5th minus 3z to the 4th plus z cubed minus z squared plus 3z minus 1. So h prime of z is going to be 5z to the 4th. And so now I'm going to stop doing that -1 thing. I'm going to go straight to the answer. I want you to get comfortable with that as soon as possible so you don't get bogged down with too many calculations. The more calculations you have to do and write down, the more chances there are for you to accidentally slip up. I've seen it happen. Like, I've seen it happen already on some of the exams where someone wrote a plus sign and then it magically changed into a minus sign on accident. Not like, I know you didn't just want to change it on purpose. It was an accident, but either way. So 5z to the 4th minus 12z to the 3rd plus 3z squared minus 2z plus 3, and then minus 0, but subtracting 0 doesn't do anything. Any questions on that? Do you have a question? Or just digesting? Next one, similar situation, since we don't, since the quotient of a derivative is not equal to the derivatives of the quotients, quotient of the derivatives, we need to divide first. But that's not too bad. This is the same thing as x cubed over x minus 2x to the 1/2 over x. I converted the square root x to exponential form because I'm going to need to simplify this. So that will be x squared minus 2x to the negative 1/2. So f prime of x is 2x minus, well, actually plus now, x to the negative 3/2. I want you to try and determine why that's true. I want you, like, if you don't see it already, that's okay. Convince yourself of it. I will talk about it in just a moment. But try to make sure, like, try and do that in your head and justify it to yourself. If it doesn't make sense right now, that's okay. But, like, hopefully the first one makes sense by the power rule. And then by the power rule here, you're going to have a -2 times the negative 1/2, which makes that plus sign, +1. And then negative 1/2 minus 1 is negative 3/2. Yes, bro. For the second term. So there's a small, like, the small mini step. F prime originally, so it'll be 2 times x to the 2 minus 1 minus 2 times negative 1/2 x to the negative 1/2 minus 1. And so the negative cancels itself out. The 2 and the 1/2 cancel each other out. And that's why I have just the 1. And then the numerator is now negative 3/2. Is that all right? Does that explain it? Thank you for asking me. Last one. We don't have a rule for 1 over w to the pi. We don't have 1 over w to the anything. We don't have a rule for it. But we do know about exponent rules that says that you can rewrite this as w to the 7/3 plus w to the negative pi. So anything 1 over can be rewritten as that thing to the negative version of that power. So p prime of w, I'd like you to try and fill in the blanks. Derivative of the first term, 7/3 w, the 4/3. And then you'll have minus pi w to the negative pi minus 1. And we cannot combine pi and 1, so we'll just leave it in exact form. Like, sure, it's going to be like negative 4.151, negative 4.1415, whatever. But we're going to write it in its exact form. Say it again. Oh, you're absolutely right. You're absolutely right. P prime. Thank you. Thank you for catching that. Good catch. All right. Next ones, we have a few extra derivatives. The derivative of e to the x is one of the best ones. E to the x. E to the x is the only non-zero function that its derivative is itself. Very, very cool fact. There's plenty of proofs of it, both calculus now and then calculus later proofs. But that's a really, really unique property. No other function has that property. No other function can you take its derivative and just get back itself. There's plenty of math memes out there if you want to see them that make that joke. The derivative of a to the x for any other base other than the natural base is natural log of a times a to the x. The derivative of a natural log is 1 over x. And the derivative of log base b for any other logarithm is 1 over natural log of b times 1 over x. Proving A and C, kind of difficult. Proving B and D they're actually consequences. Now I can tell you 100%, as a note, you don't need to have B and D memorized. But C and D, A and C need to be. A and C are just too common. Like, I need you to have them memorized. The other two, B and D, what frustrates me, like, I can tell you firsthand, I've never seen in the real world the derivative of a to the x. Never seen it. Never seen it once, or log base b. It might happen, but the fact of the matter is that any exponential can be rewritten as a natural base. So a to the x, you can just write this as e to the ln of a to the x, which is e to the ln of a times x. Boom. You've got a natural base now. So, like, you don't need to write that down. You're not going to be tested on that. But this is why I don't like memorizing that fact, because every single exponential function can be rewritten with a new base of e. And same thing, log base b of x is the same thing by the change of base theorem, natural log of x over natural log of b. And that's actually why the derivative of d is 1 over ln of b times 1 over x. Just a fun fact. Getting to bust out that change of base theorem, right? Super cool. Change of base theorem. Most important theorem, not really. So useless now, sadly. Back in the day, like there used to be textbooks that had log base b for like a bunch of different values and a bunch of different approximations. It's like a chart of natural, like log base 5 of 7. And then it gave you an approximation and you had to use that chart on your exams. Good time to be alive, but not really. Okay, so this one, the derivative of e to the x plus 2x cubed minus 7x, 7 times the 5th root of x plus log base 7 of x. As a small little aside, when it comes to exam time, if you're ever concerned, you can always ask. Some students mistake that as 75 square root x, especially since it's tiny on the exam, or they're just reading it too quickly. So please feel free to ask for clarification. I'm happy to tell you that is 7 times the 5th root. So I'm going to rewrite that right off the bat. This is the same thing as negative 7x to the 1/5 so that we can find this derivative. Y prime or dy dx, however you want to write it. The derivative of e to the x is itself, e to the x. Derivative of 2x cubed should be 6x squared. The derivative of negative 7 times the x to the 1/5 should be negative 7/5 x to the negative 4/5. And log base 7, that's that property up there. That's plus 1 over natural log of 7 times 1 over x. Any questions on that? All right, next one. 3 natural log of x. That would be, so g prime of x would be 3 over x. The 21x, that would be minus natural log of 21 times 21 to the x. And then the derivative of 5 would be 0. So that's all we have for that one. And just so we're clear, I've just thrown 10 rules at you. So it's okay if it's taking a second. I don't expect you to know these overnight. These take practice to do. And the best thing you can do for yourself, right? Like maybe an hour, like after your next class or whatever, just do like 2 problems. Go to Paul's online notes. His questions are usually a little easier than mine. Go to Paul's online notes, look for the basic derivative rules, look at the sample problems. Just do like 5 of them tonight, please, for me. It will make your life a lot easier. All right, now we get to some application problems, fun stuff. Determine the values of x. So we're not looking for points, we're just looking for x values for which the function h of x equals 2x cubed minus 1/2x minus 15x plus 3 has a horizontal tangent line. So whenever you're encountering a problem that you don't know what to do with, try and think about what you do know. We're talking about a horizontal tangent line, which means we're probably going to have to take some derivatives because the derivative gives you, like at any given value, will give you the tangent line. If it's a horizontal tangent line, that means that m tan equals what? 0, because a horizontal tangent line has a slope of 0. So, need to solve h prime of x equaling 0. That's what we're going to do. What this question is asking us, without asking us, is to set the derivative equal to 0 to find where your derivative, your slope your tangent line would have a slope of 0, i.e. a horizontal tangent line. There's that level of deduction that I love. It's fun. So h prime of x is 6x squared minus x minus 15 and then plus 0. That doesn't do anything. And we're going to set that equal to 0. And you can use whatever method you want to factor it, or since we're not going to really be doing anything with the factorization, you could use the quadratic formula. Anything's fine with me. This should be 6 and 1 should not work. So 3x, 2x, 3 and 5 minus plus, right? Negative 10x plus 9x. Yeah, good. That's the only way that's the way I learned to factor. I learned to factor by the trial and error method. Teacher just took a bat, hit us when we didn't figure it out. Mrs. Arrington. Hard time. She didn't actually hit me with a bat. She was a great teacher. But that's the way we thought. So don't worry if you don't do the like AC method, box method, whatever you want to do is fine. It's bottoms up. So x equals 5/3 and negative 3/2. John Doe student boxes it in, and John Doe student is finally right for once in his life. Because it's only asking for the x values. It's not asking for the points. If it asked for the points, we plug those x values into H, find the corresponding y value. The next one, super cute problem. But this one right here, this one is a doozy. This one probably take us about 15 to 20 minutes tomorrow on Thursday. It's an excellent problem though. But this one, super cute. Find the equation of the line tangent to the curve f of x equals 3x squared and perpendicular to the line 3x plus 18y equals -7. Yeah, we got 10 minutes. So we're right on track. Find the equation of the line tangent to the curve f of x equals 3x squared and perpendicular to the line 3x plus 18y equals -7. When we first encounter a problem that we do not know how to solve, we ask ourselves, what do we know? We're trying to find the equation of a tangent line. A tangent line needs a slope and a point, right? Let's start off with slope. So it needs slope. Since perpendicular, does everyone know that symbol? Upside down T to mean perpendicular. You can write perpendicular or perp or whatever, but since perpendicular to 3x plus 18y equals -7, we need to know that line's slope first. Because if we don't know that line's slope, we're SOL. That line is in what we call general form. We want it in slope-intercept form because the slope-intercept form will give us the slope. So 3x plus 18y equals -7. That would give us y equals -3/18. That's -1/6. X minus 7/18. Yeah, that's not a pretty fraction for the -7/18, but we don't care about that. That's the y-intercept of the line that we were given. We're talking about our tangent line. The tangent line is only going to look at that slope. So m perp, or m upside down t, whatever you want to write, is equal to -1/6, which implies that m sub tan, since our tangent line is perpendicular, would be the negative reciprocal. If you know that little trick, you just flip the fraction, change the sign, or you can do it like via the math. That would be -1 over -1/6, which is +6. But the quicker way is just to flip the fraction, change the sign. So M10, oh yes, Chris.
I fell behind for a second. How'd you get the slope?
Excellent question. So there's a little mini step here. Let me add it in. So this becomes 18y equals -3x minus 7. And then I divide both sides by 18. So the -3 gets divided by 18, which gives me the -1/6. And the -7 gets divided by 18, which just gives me -7/18 because there's no common factors.
Thank you.
Yeah, excellent question. Thank you for asking that. I was looking at it, I was like, I think I should probably draw that, but I didn't, because I didn't want to get carpal tunnel. And I'm lazy. Which all mathematicians are. Every mathematician I've met is lazy in some way, shape, or form. So now the thing is, we already found the tangent line slope. We found m tan, and we didn't even need to find the derivative, right? We already found m tan. So we didn't even need to find the derivative. But wait a minute. There was no point given. We must be able to find it somehow. And that's where this comes into play. We know that the tangent line has to have a slope of 6. But the the derivative will be a function, which will have x's in it. That will allow us to solve for x, which will allow us to find the point. So, since m tan equals 6, that implies that f prime of x will equal 6. So f prime is 6x equals 6. That implies that x is equal to 1. We have found an x value. So we used the derivative function to find the corresponding x value. That function, that curve, if you were to draw 3x squared, you'll notice, and sorry, people watching the recording, once again, talk to me about this if you want to know. You'll notice that this function has a unique derivative everywhere. Every single time it just keeps going up and up and up. You're never going to get a repeated slope. You go to the left, you're going to get negative slopes. They're going to be symmetric, but every single slope on that of a tangent line will be unique. That's why we only get one x value. So we found the x value, but we still need the point. So f of 1, not f prime of 1, but f of 1, because we're looking for a point on the curve f for the tangent line. F of 1 would be 3 times 1 squared, which is equal to 3, which gives us the point 1 comma 3. So now we have slope, we have point. We can write it y minus y sub 1, so y minus 3 is equal to m, which is 6, times x minus x sub 1, which is 1, or y equals 6x minus 6 plus 3, so minus 3, 6x minus 3, or any questions? 1 squared, yes. You can't tell that that's a 2. That's not like that. That's clearly a 2. That's not an L. It's 2.
Less than sign.
Yeah, it's definitely a less than sign. There we go. I'm just being cheeky. Okay. So we've got 4 minutes, but this problem, as I said, is going to take us about 15 to 20 minutes to start. It's a long problem, because we're going to be talking about it the whole way through, and we're going to be doing a lot of algebra and arithmetic. It's a really, really cool problem, and I'm very excited to talk about it, but we will talk about it on Thursday. As a reminder, we have a quiz on Thursday. It's just on 2.1, so no 2.2 on it. You can use 2.2 to verify your answers if it's possible. But we will be doing, we'll be starting that up at the beginning of class, and then we'll be starting up 2.2. We'll finish 2.2 and go on to 2.3. If you guys have any questions, feel free to email me. I'll be handing back those exams on Thursday, so next time. All right, guys, if you have any questions, feel free to ask. Otherwise, you guys have a great rest of your day, and I'll see you on Thursday.